we talked through the material in lesson 40, the laws of logarithms sound familiar to you. The first part of this lesson, most of the lesson, will be reviewing these properties that you learned last year and you used to solve logarithmic and exponential equations. So hopefully it'll come back pretty quickly. We also will talk about what I referred to from that one homework problem of verifying that functions are inverse functions. So first is reviewing our vocabulary. Argument is the input value for the function. It's what gets plugged in. If we are talking about the log of anything, whatever is in the parentheses is the argument. And for logarithms, the argument must be positive. So it can't be negative and it can't be 0. So we look at our answer and we put it back into the parentheses, and if it makes not necessarily if the number x, or if what we get for x is negative or 0, but if we put it into whatever expression is in that parentheses and get a negative or 0, we have to throw that answer away and not count it. Maybe we have another one we can keep, or maybe we have none. Also, inverse functions undo each other. We start with x, we do one function, the inverse undoes it and gets us back to the x that we started with. And it has to work both ways. So you're going to be seeing homework problems that say, verify that they're inverses. Show whether they are or are not inverses. You do not take one of them and switch y and x and solve. You show both compositions, f of g and g of f, and show that you get x both times. It is not just that you get the same thing. If you get 2x for both of them, they are not inverses. You've got to get just x for both of them. And you have to show it both ways. If you do one, though, and get 3x minus 1, you didn't get x. If one of them isn't x, then you can stop. If you trust yourself and think your work was correct, and say they're not inverses. But you can only say yes after you show it both ways. So, to get our log properties, we want to remember that logs and exponentials are inverse functions, and we want to remember how we work with exponents. So first, if we are talking about logs and exponentials being inverses, that means they undo each other. So if we have a log that is an exponent, if we exponentiate that, so we have 6 log 6, or whatever our base is to the log of that same base, it becomes just the exponent. The 6 to the log 6 cancels out and leaves just the exponent. It also goes the other way. We can have something that is raised to a power, the 6 cubed, and if we have the log base 6 of that 6, it cancels and we just have the exponent 3, or the log base b of b to something cancels and we just have the n left. So either way it cancels out. And we'll use that a lot to solve different equations. For our other properties, we are remembering that if we have 2 arguments that we multiply, that's when we would add the exponents. So remember, exponents are logs. So if we're adding logs, we're adding exponents, which comes from when we multiply the arguments. We also remember that if we are subtracting the exponents, that was because we had a division of the arguments. So since the exponents are logs, if we are subtracting the exponents, we're subtracting the logs, which means we need to divide the arguments. And we'll put these properties in log form on the next slide and into your formula list. And our last property if we have something that's raised to a power, and then we multiply that by a number like the 6, and this should have been a times in here. Not sure why that dot moved where it did. If we multiply a log by a constant, so we're multiplying that power by the constant, that means that the original argument was raised to a power. So we took this original exponent, exponents are logs, multiplied it by a constant. That was the same as if we raised the argument to a power. So here's what those look like in log form. Raise your hand, nod your head. Do these kind of sort of look familiar? Yeah, we saw these last year. I'm not saying could you have used them without review. Do you remember them that well? But, oh yeah, we at least worked with these kinds of things. So if we have two logs that we're adding, so we're adding the exponents, that was when we multiplied the arguments. And these go both ways. If we start with the log base b of mn, if we multiplied the arguments, that meant we needed to add the exponents, so we add the logs. If we are subtracting the logs, we're subtracting exponents, we did that when we divided the arguments. If we have arguments that we're dividing, we know we need to subtract the exponents, so we subtract the logs. Again, we can go either way. Last one, it also goes either way. Easiest way to think about it is if we take an exponent times something, that means we have one argument raised to an extra power, so we take the argument and raise it to that power. It is important to remember on all of these, it is the same base all the way through. Can't have one base on one side and one on the other, or two different bases on one side and combine them this way. So let's try these out on some different problems. Do I have the same base all the way through this? That means on the left, I added my logs, I added my exponents. That happened when I multiplied the arguments. This step is required. It's not mental math, just skip that and go to the next one, because I see too many mistakes. I want you to write down how you put the logs together on one or both sides, depending on how complicated the problem is. Then you can think of this as two ways, in two ways. If you have log 80 equals log 80, not log 80 plus log 80 equals, but just one log equals one log with the same base, you may set the arguments equal and write down that the arguments are equal. The other way you can think about it is using that logs and exponentials are inverses, so let's exponentiate both sides. By that I mean, since this was a log base 80, let's make this whole thing be the exponent of an 80, so 80 to the log 80. If I do that on the left, I must do that on the right, and the 80 log 80s cancel out, and we just have the arguments, 49 equals 9 plus x. So everybody, what is x? And then we check up here. This argument's positive, this one's positive. 9 plus 40, is that positive? So we're good, we keep that as an answer. Mentally, yes, you don't necessarily have to write it down. But you're going to lose points if you don't do it, because some of them are not going to work. Okay, do I have the same base all the way through? Who can tell me what property I'm going to use for the 4 that's out in front? Because this is not log b equals log b, that 4 is in the way. I've got to get log b equals before I go on. Luke, can you tell me what I need to do with that 4? From one of those 3 properties we wrote down in the formula list, when we have a 4 out in front of the log, what can we do with it? I'm going to subtract if subtraction and division are going to go together. When we have it out in the front, it means we're raising the argument to that power. So we have log base b of x to the fourth equals log base b of 81. I have log b equals log b, so my arguments are equal. Or I think of it as exponentiating both sides. Both of those are now exponents for b, and b log b cancels out. If x to the fourth is 81, what can x be? Okay, technically, if we started the problem right here, x could be 3 or x could be negative 3. Both of those to the fourth would be 81. However, when I come up here, 81 is always positive, 3 is positive, negative 3 is not. So I mark it out either with just an x or with just half of an x, one line. I still want to be able to see what you had. Don't erase it. Just put a line through it. Argument must be positive as a reason for what's going on. Questions from anybody on that example? Going on.
So on the homework, you say, right, argument must be positive.
Yeah, you can abbreviate it to make it shorter.
Does the argument always have to be positive?
The argument for a log always has to be positive. And that's what's important in solving log equations. That's what you've got to go back and check for. What else, Allie?
So how did you get rid of
If you have something to an even power, you have a positive and a negative. Like if you get to x squared equals 9, you have to do the plus or minus square root method. If it's any even root, you've got to do the plus or minus, except in this case, the minus doesn't work because it came from a log equation. All right, I'm going to get back to the next example. Okay, same base all the way through. Okay, this one I am subtracting logs. So what does that mean I do on the left if I want to combine those so that I just have one log in there? What am I going to have to do? I need to divide them, and it is log base 6 of x plus 1 over x minus 1. It is not the log of x plus 1 over the log of x minus 1. It's one log of the quotient. Equals log base 6 of 3. Log 6 equals log 6, so arguments are equal. What we really did was we exponentiated both sides. 6 log 6 cancels. So when I have x plus 1 over x minus 1 equals 3, now what do I do to solve that? What am I going to do in that case, Faye? Multiply both sides by x minus 1 or take the cross product, whichever way you prefer to think about that. And we have 3x minus 3 equals x plus 1. Subtract x on both sides. Add 3 on both sides. Divide both sides by 2. X is 2. We go back up to the top and check it, and we're always checking in the original problem. That does not necessarily mean the first thing you write in your problem set box. Because sometimes you look at it and you do the first step and write it down. Go back to the original problem, wherever that is. 2 plus 1, is that positive? So we're good. 2 minus 1, is that positive? So we're good. 3 is always positive. So this one works just fine, and we keep the x equals 2. Notice on that, I did not say x is positive, so it works. I went back and checked what happens when I put the 2 into those arguments. What do I get? Okay, a couple more examples here before we move on to general inverse stuff. So, same property that I just used. Log base 4 of x plus 3 over x must write down. What does it equal on the other side? Just a 4, not a log of 4. This is why we write it down, because we make too many mistakes if we try to do it in mental math. We try to write down x plus 3 over x equals 4, and we forget that there wasn't really a log on the other side. So I can't set arguments equal to each other because I don't have arguments on both sides. What I must do on one like this is to exponentiate both sides, so make both of them the exponents of 4. So on the left, 4 log 4 cancels, and I have x plus 3 over x equals 4 to the 4th. 16 times 16, 256. Cross product or multiply both sides by x, and we have 256x equals x plus 3, subtract x on both sides, 255x equals 3, divide both sides by 255. Can I reduce? 5 plus 5 plus 2 is 12. That's a multiple of 3, so yes, I can divide 255 by 3, so it's going to be 1 over 85, I think. Then we go back and we check that up in the original arguments. 1 over 55, or 1 over 85 plus 3, that's positive, right? 1 over 85 is positive, so I'm in good shape, and I keep that for my answer. Okay, last one, and then we do the inverses. Both sides are log 45. What do I do with that 2/3? What do I need to do with that? I need to, well, it's not really exponentiating both sides, but it's making that become the exponent on the 27, so that we have log base 45 of 27 to the 2/3 is log base 45 of x. Log 45 equals log 45, so x equals 27 to the 2/3. Or we think of, we exponentiated this row and made both of those be powers of 45. So far, so good. And then that means we take the cubed root of 27 and square it. What's the cubed root of 27? Square it. And 9 is positive, so we keep that answer. Right, you can do that on the log problems, which are great so far. Okay, last problem. It's got to, the composition has to work both ways, and I need you to label which is which so that I know what we're doing. Show whether they are inverse functions by computing their compositions, not by switching y and x and solving for y. So we are going to label. So I need to do f of g of x. It's enough labeling to do f of, and then I can write g of x, the 3x plus 9 in here, to tell me this is the one where we're plugging 3x plus 9 into this rule. So just this x becomes a 3x plus 9. We keep the 1/3. But now instead of times x, it's times 3x plus 9. And then we still have this minus 3 out here at the end. It is not mental math. Write down the work. Distribute the 1/3, and we have x plus 3, and then minus 3. The 3's cancel, and we just have x. So far, so good. But that's only one way. We have to calculate the other composition, which means g of, and this time we're going to put f, the whole 1/3 x minus 3, in where we had an x in the rule for g. So we're going to keep the 3. We're going to put, for this x, 1/3 x minus 3. And then we're going to keep the plus 9. We're going to show the work, distribute the 3, and we have x minus 9 plus 9. The 9's cancel. And again, we have x. So therefore, we write down f and g are inverses. If I did f of g of x and I got 2x minus 1 and felt confident in my work, I could jump straight to f and g are not inverses and not have to calculate the other composition. Anybody with questions?